Hi everyone, welcome to my tutorial on how to run parallel processing in R programming. I want to keep this really quick, so I'm just going to get into it. So I start this with every script. So clear the working environment, set the working directory to the source file location. I put it in this little loop because if you run this in Bash or with the terminal, uh, it'll error out unless you, of course, have it like that. The libraries I've used for each before. It's another way of parallel processing in R. It's pretty easy, but it's not quite as quick and slick as parallel. Maybe I'll do one in the future for each. And then, of course, ggplot2 to plot our stuff. ggtext and ggextra are nice little packages that I use to make clear, crisp plots. All right, so let's ground all everything up to here. This is just some metadata. Don't really worry about it. I can show it to you. Basically, we have these samples called lidpids, and then these are their sample characteristics. So like female, male, whether they're fixed or not, etc. This is dog data. Percent methylation. So I've been working a lot uh, with DNA methylation data, and so it looks something like this. Of course, these data frames are big, but you have this region from this start to this end on chromosome, right here. And then here's these lidpid samples, the columns again. That's right. It's quite a big matrix. So for this, so that I don't crash my personal computer, I'm just going to subset it to 1,000 random regions and 300 random samples. Okay, and we'll just use a variance partition example. All right, so metadata, I want to make sure everything's numeric or factors or whatever like I want. And also I'm going to be working with a specific cohort. I don't think it's really important to the viewer. So let's get down to actually how to parallel process. So this variance partition function, I'm actually going to wrap in a function of my own where I'll pass in a chromosome, the percent methylation matrix, the design, which is just age plus sex in this case. And it'll draw that design from the metadata. So here we'll parse the percent methylation for each chromosome one at a time. And so if you noticed in the percent methylation, everything started with this. Of course, if I was like, okay, if it starts with CHR1, I'm also going to accidentally grab CHR10, 11, 12, etc. So in this little wrapping function, I just paste a little underscore so that I make sure I'm grabbing chromosome 1 and not all the chromosomes that start with 1. So I'll parse that, then I'll parse the metadata. This won't be a step that you would need to use if you skip this sampling of the columns right here. If you don't know what I'm referring to, don't worry about it. It doesn't add really any computational time anyway. And then you actually do the variance partition here. I'm going to do it in parallel. Because the idea is we'll run this function in parallel for each chromosome that we have in our percent methylation matrix. So here are all the chromosomes 1 through 38, and then chromosome X. And so here's actually how to run it in parallel. So we use parallel or mclapply from the parallel R package, and we'll run the chromosomes in parallel 4 at a time until it's completed. So if you, for whatever you want to run in parallel, that should be your first argument in this mclapply, and you can make that line up with the first keyword argument in this function. But so you have mclapply, we have our chromosomes, which will actually be what we're paralleling, the function, which of course I just defined right there, and then any other subsequent keyword arguments. So percent methylation form metadata here, percent methylation form metadata, which I have all defined outside of this function, and then the number of cores to use. So I'll run that. Oh, I got all errors. Did I just not do this? Oh, what did I do? I didn't run that. There we go. Oh, still got all errors. What the hell? I'm running out of memory, maybe. When in doubt, restart, start again. All right, so that time it didn't error. So yeah, must have been that. And so then you can name, so it'll return a list of all the elements. All right, if I go, should be that, which is of course the same as our length of our chromosomes. So then you can just name all of them the chromosomes. So one in this case is going to return the same thing as when I named it. And then I can bind them all together pretty fast. That takes no computational time. I'm going to do some gsub, beautiful parsing. This is a little trick that I do with ggplot. So I define, so if you've ever worked with ggplot2 in R, like you would be able to add like theme minimal as to a ggplot object or whatever. I just add my own theme, and then I can include it in my ggplot object because it's just nice. It's just nice to like have my own way of doing things. Okay, and so now, of course, here's the output. So we have age, sex, and then residuals. So this data in particular has a lot of high residuals, but age and sex are able to capture some variance in some of the regions that we've done. So thanks for watching. I hope this was helpful. And yeah, MCL apply. It's pretty slick.